Logarithms then. So let's have a look at our logarithm function. Now, there's, I guess, a definition of what a logarithm is. So the logarithm of any number to a given base is the index of the power to which the base must be raised in order to equal the given number. What a mouthful. What on earth does it mean? Okay, so if n is equal to a to the power of x, then x is equal to the log of n base a. That's what it's really saying. So they're inverses of each other. You'll notice the base stays the same. So in the first line, the exponential has a base of a. In the second line, the log has a base of a. So now let's look at that definition again. It might make a little bit more sense. The logarithm of any number to a given base, so we have log n base a, is the index of the power. So x, if you have a look at the first line, is the power. So that's what it's basically saying, is what power do you need to raise the base to get this number? Is essentially what it's saying. So we get a question like this. The question is really saying 10 to the power of what is 1,000? Of course, another way we can simply solve it is to do the inverse. So to undo the log, we turn it into an exponential, but the base has to stay the same. So now the base goes with the x, but x becomes the power. So 10 to the power of x is 1,000. Oh, yeah, okay. X is equal to 3. So this one, the base is 5. 5 to the power of what is 1 on 25. That's essentially what it's saying. So to undo it, there we go. 5 to the power of x is 1 on 25. That's negative 2. This time we've got to find the base. So we're saying x to the power of 2 is 64. But notice in this situation, I don't write plus or minus 8 for the answer. Go back to the definition. When we're dealing with logs, a has to be greater than 0. We only have positive numbers for the base. So in this situation, x is 8. Negative 8 is not an answer. And this one then says, well, the base is 6, so 6 squared is equal to what? Well, 6 squared is 36. So some rules that allow us to manipulate logarithms. So the first one, the log of a to the power of x base a is equal to x. Because we're saying a is the base, a to the power of x is equal to a to the power of x. Well, this is true. Second one, this allows us to cancel the inverses. So if you have a to the power of a log the same base, then they will cancel and you just get left with x. But reminder, x has to be greater than 0 for this. Those first two really are just dealing with the fact that logs and exponentials are inverse functions. This one here, these next log laws really just go back to the index laws that we already know. It's just a rearrangement of them. Because this one here is really saying a to the power of 0 is equal to 1. The next one, log a base a is 1. Well, that comes from the fact that a to the power of 1 is always a. Log x plus log y, if they're the same base of course, is the log of x times y. That comes from the index law that says, well, when we multiply together, we add the powers. And we have a similar one for division. So log x minus log y is the log of x divided by y, coming from that particular index law. And this one here, the log of x to the power of p, we can rewrite as p log x. That certainly comes in handy when we're solving exponential equations. But that comes from the basic index law of we multiply in that situation where we have the parentheses to a power. It allows us to work out things like this. So log 20 plus log 5, well, it's a bit hard to work out. 10 to the power of what is 20? It's not a nice, neat number. Similar with 10 to the power of what's equal to 5. Not a nice, neat number. But if we use our log laws to combine those, we end up with 20 times 5, which is 100. And then that is a simple one to work out. 10 to the power of what is 100? Oh, well, 10 squared is 100. Division 1, again, 2 to the power of what is 18? Well, yeah, I don't know. Combine these together, we end up with log 2 base 2. Well, a number to its own base, the answer is always going to be 1. All three combined here. We've got a plus and a minus. Well, I can combine it. Plus we know means multiplication. Subtraction, what I'm actually subtracting there, I need to move the 2 into the log before I can use my log law. So that's really the log of 6 squared. Hence, we end up with 6 squared on the bottom of the fraction there. So 9 times 8 divided by 6 squared turns out to be 2. 4 to the power of what is 2? Well, 4 to the power of half, because the square root of 4 is 2. We've been given 2 logs, the actual answer. Right? So they're telling us that basically that 10 to the power of 0.3010 is 2. Well, it's probably an approximation, but it'll be pretty close to 2, I imagine. And 10 to the power of 0.4771 is equal to 3. Again, it's an approximation. Oh, someone's pulled out their calculator. How close does it get? Like very close. There you go. Told you to be very close. So from that, let's work out log 27 base 10. So 10 to the power of what is 27? I basically need to rewrite 27 in terms of 3 and 2. I suppose I could use 10 as well, because we know log 10 base 10 is 1. But other than that, we pretty much don't know. 27 I can rewrite as 3 cubed. Then I can bring the power to the front. 3 log 3. We know what log 3 is, so we can now work it out. So again, 10 to the power of 1.4313 would approximately be 27. Square root of 2. Well, I could rewrite that as a half log 2. And so we get a half of 0.3010. 12. I can only use 2 and 3. Oh, and I suppose I could use any one that I've now worked out as well. Although in this case I don't know that's going to help me. 12 is, oh, of course, 4 times 3, and 4 we can rewrite as 2 squared. So log of 3 times 2 squared, so I can rewrite that as log 3 plus 2 log 2, sub in the numbers that we know, and we get 1.0791. All right, 8C and 8D.